integrated circuit 19, digital circuit pipeline versus parallel computing. So let's try to clearly understand what the pipeline architecture is and what the parallel architecture is. Okay. Now, pipeline is basically using conventional CPU. You time slice each task. Okay. That means you have register here, register here, register here. Why you do that? Because when you have the operation like the add A1 B AIBI and repeat this 1,000 times, each operation you go through and start the next operation takes too long time. Okay, remember the multiplier is a huge hardware. We already talked about that. And if you don't time slice, it takes long time to finish one and come back and start another. So like production line, the car manufacturing, they finish engine, door, whatever, each conveyor you do the task. So in this way you can finish the car like every 10 minutes, one car. Okay, but to do that you have to time slice, and that means CPU clock, the clock is say 100 nanosecond to 1 nanosecond. Every 1 nanosecond you get one calculated in this architecture. So this was the idea of a pipeline. Okay. Now parallel is you put all the data and move this each data A1, B1, A2, B2, so and so, and do the calculation, right? So you can do it in parallel, and if you have 1,000 of CPU, the 1,000 parallel computing is going to be faster than this one. But the problem is to move this data to each, it takes time. So this register need to have multiple port, so it can read the data from each section of register at one shot. Okay. Now it's possible to combine pipeline to the parallel architecture because you can time slice this each one. Okay, but the problem is parallel computing, you have to coordinate distribution of task. It's get pretty complicated. On top of that, each one is time sliced, so you have to keep track of this factory, Nissan, Toyota, GM, every factory at the one shot. So it's get complicated. If you can handle this, then you can combine them together. They are not, going against each other. But disadvantage is what's happened if you have a dependency. Dependency is add A and B, result goes to C, then you add D to the result C. C is A plus B. Okay, without calculating this, you cannot move on to the next instruction. This is called a dependency. The C depend on A and B, right? And in this case, this pipeline fails. and this parallel architecture doesn't show any advantage. You have to finish this first before moving on. Okay, so that's a kind of problem we have. Now here we can have an independent register, but the preferred method is to use a cache. What's cache? The cache is the, from memory viewpoint, you have only, let's see, it's not helping me. Okay, here the memory has a data, and the cache is a high-speed memory. And what's happened is you stage some of data. This size is smaller, so you cannot stage everything. Then CPU use that. Okay, and CPU does the job and bring it back, and immediately it's going to be transferred back to the memory. Okay, so this is a cache. The cache is transparent from the data viewpoint. It's there, but all the data should be here, right? So there are many kinds of cache. Okay, the read-only cache, that means you put the stage the data, and CPU use it for reading faster reading. Okay, but when it's write down, whatever you write back is immediately written back. Okay, so it's called a write-through cache. If CPU just write it in memory directly, then it's read-only cache. If cache write it back to memory right away, then it's called write-through cache. And the read-write cache, that means you stage the data and the CPU work on it. You keep the new data here. It's not in the memory. Okay, then what's happened is this data need to be written back to memory sometimes, and the memory to the hard disk, permanent disk, right? Otherwise you may lose the data. Okay, but this way it's faster operation. This gives the fastest operation, but a little risky because the data is not written to the memory, means that not written to the hard disk. Okay, so that's called a read-write cache. And also, when you have a multiple CPU, this CPU access memory too through cache, then you have this consistency issue. If you change the data here and doesn't write it back, then this guy has a different data, so they see the different data. So what you do is you have a cache management monitoring anything the written back. It's go back to the memory and update this guy. So the cache management operation become the consistency operation, means it has to read it and write it on the back of the cache, so that every CPU sees the same data from the memory. Okay, and this cache, then which block of data you're going to stage. The algorithm, there are many algorithms. There's a FIFO, the LIFO, and round robin and prefetch. There are many techniques used. The details you have to go through the computer book, but those are architecture. Now this extended cache become necessary for this kind of parallel computing, because data is all over in each CPU, and 1000 CPU. Basically, on the board, you have 200 CPU, and you have 100 board like that in a supercomputer. Okay, now the going back to this dependency, fortunately, most of the problem has very little dependency. The reason is it's a matrix calculation, and you know matrix calculation is just multiply and add this. Okay, the scientific calculation numeric method is to use the matrix repeated many times, and it's need a supercomputer to do scientific, because matrix calculation of floating point. Okay, but they have AI single chip and video accelerator chip, so that can be done in a single chip. The reason is they don't use floating point. They have a limited range of integer, so the CPU is small, much smaller, so many of them fit into single chip. That's AI chip. And the video accelerator chip doesn't have to be floating point. Why? In order to decide the position in a 3D after, say, rotation or expansion, do you need a floating point? Well, actually, in the real world, you have a limited resolution on the screen. So if you have a screen size limited, that's an integer. So this integer, you don't have to go decimal number to do the graphic manipulation. You can use integer. Decide from this point to this point. The dot move from one point to another point. So integer only manipulation, the mostly matrix calculation, can be done with a small CPU, which fit, the many of which fit in a single chip. So those can be single chip. But scientific calculation, you have to do matrix calculation on floating point. Okay, so that's require this kind of large scale supercomputer. Okay, so doing the AI work using supercomputer is kind of overkill. The AI chip, it should be the chip, LSI chip, and that does very well, because the matrix calculation, the number used in matrix calculation, the range is limited. Okay, so that's overall architecture of CPU chip. I hope you like this video, then subscribe.